Before I dive into what I've learned so far, I would like to just give some context on how I started learning neural networks and also like what my background was and how much study I did beforehand. So we're sort of on the same page. You are also, if you are also learning and would like to share your journey. So I did these Andre Kapadi's course, and these are amazing. Yeah, it is still like I can't believe these videos are there for free for us to watch. And if you don't know Andre Kabadi, so he played a major role in building Tesla full self driving um, neural network like stack and the whole thing there. It's just not. It's not just the neural network stack. There is a lot that goes on, and I think Andre played a big role on training the network there, and he's now in OpenAI, I think. And after that, I did this course on computer vision, Buffalo Online on Coursera. So this was by, I think the professor of this video was by Buffalo University. Anyway, it has some tie to Buffalo University. And this is a really good course, and it goes back um, and it teaches you like how digital images are made, like recorded and all that. So it's a really great course to do if you want to do that. So yeah, that's pretty much it. What I've done so far, and I don't have a strong background in math, and yeah, I say like I struggle a lot. So which is why I wanted to learn and go through each line of this code and just try to explain them as I learn, because I find like explaining is very hard. You can just sort of read something and tell yourself that you've understood something, but when you really start to explain, you realize you've understood either half or less than half of it. So, and a lot of these classes and method, they do a lot in terms of like math, and also like a lot of um, a lot of complexity is hidden underneath. That's what I was trying to say. So deep diving into each of these will help understand, and I think you can only become better by understanding what really happens under the hood, and gives you a better insight when you're building or working with the model in future. So that's my intention here. And today what we're going to cover is the Softmax method and what it does. But before we dive right into that, let's just go through what we did in so far. So we've understood how this code gets executed here, and we have this ReLU stack. So once we pass in the input, it gets so we don't call this forward method, but it gets passed into this forward pass, and then it returns us the logits, and these logits are the output of this network will be 512 by 10. And if we go down and look here, we create a model instance of this neural network class, and then on that model instance, so here we are passing the x as an input, this input tensor here that we created, and what returns, what this model returns is the logits, and logits are the output of the model. And here we create an instance of this softmax class, and then so once we create an instance, then we call on that instance and pass these logits that came from the model here. And what we get out of this is a probability distribution. What does that mean? So to understand that, let's look at this example here. So just to create some simple example, we created again a softmax instance here, and then we create some input tensor which is 2 by 3, and then we pass in the input to the softmax instance, and we got the output. So now let's analyze here for this first tensor what's happening, right? So our input tensor had the first on the first 0th index we had element 0.6937, negative 0.351, and 1.056. And when we pass it into softmax method, what happens is we get probability distribution of these numbers, of each number in this context of this whole tensor, right? So for example, this number has 0.30, so 36% of this number appearing on this tensor, and we have 12% chances of this number appearing in the tensor, and also 50% chances of this number appearing in tensor. And you can also like relate to it based on looking at these numbers. So this is a negative number and it has a lower probability. Higher number has a higher, slightly higher number has slightly higher probability, and the highest number has the biggest probability of 50%. So that's how we get the probability distribution. And if you look at this output tensor returns 10, and what it's trying to do is trying to give us a, well, eventually we will get a probability distribution out from that output tensor, which are the probability of that image being one of these class. And that's how we understand whether what we got in probability versus what it's supposed to be by the label, the training data, and then we keep going backwards using back propagation and then forward pass. So we adjust our weights and biases until we predict the right item. So now I just said a lot of things there, and let's take a step back and look at this softmax method, what it really does. So I just wrote that in Python just to clearly understand. So I'm not using any tensors or anything here, just a simple Python list. And what this method takes is the list of numbers, which is this here I passed for this example. And what we first do is we iterate through each of the number and exponentiate the number. And how do we exponentiate a number? We use the power method, and we pass in this Euler's number, which is, you can just Google 2.71828. So the value of E is the mathematical constant, which has been used in many branches of mathematics and physics for years. The number is approximately blah, 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 and is the base of natural algorithms, right? So we use that number to exponentiate here. So let's go back, and then we pass in each value. So on this exponentiated new list, I'm appending each value as they are exponentiated. And once they are exponentiated here, I'm just getting a sum of the newly exponentiated values. So sum of all the values. And then again, what I'm doing is I'm iterating through these exponentiated numbers and then dividing them by the sum of it, right? Sum of that exponentiated numbers. And what we get in return is the probability distribution we just talked about. So here again, you can relate 1.6, the highest number has 82% chances, and then 0.04, the negative number, which is slight, quite a negative number comparison to this, so has 14%, and the highest, like the smallest number, has the 0.03% of probability. So, and as you notice, when we sum this up, it should always sum up to 1, being the 100%. So when you distribute across the entire tensor, or the number of item in that tensor, they should always sum up to 1, being, when you combine all the probability distribution, it should be 100%. So that's what the softmax method really does. And obviously there are a little bit more complexity if you look into the source code of the softmax method. And if you compare this with the PyTorch result, they can be slightly different. And I'm guessing that has something to do with this Euler's number being used, and how the numbers are exponentiated, right? So yeah, that's what the softmax method does. And in the next video, I'm going to go through the rest of the code. I hope I made some sense there. And again, if you're also learning neural network, please feel free to share your learnings and correct me or add some more explanation to help understand and help each other in this journey.